We're now going to start section 5.2, which introduces mathematical induction, which we're going to be doing throughout the rest of this chapter, and it is a fairly long chapter. Many students find that math induction is one of the more challenging topics in this class. But I want you to realize it's also one of the things that if you go on and you take an algorithms class in any form, it's something you're definitely going to use. So this is a skill you really need to learn. Before we start doing examples, which we'll do in the next video, let's talk about this idea of mathematical induction. It's defined for you on page 246 of your text. And the principle, and first of all, a key word is that it is a principle. This is not a theorem or something we're proving. This is something that we are assuming to be true. What we're going to say is that if there's any property, like P of n, that's defined for a group of integers, or for all integers, actually it could go on forever, and you have some starting place, which we'll call A. A is some fixed number that's the beginning. That beginning, when we work with arrays in computer science, is almost always 0. In a lot of the problems we'll do, we'll be starting at 1 for doing works with mathematical induction with a pure math form, but not all problems start at 0 or 1, and we may see some that are a little bit different. What you do is you say if the property is true for the first one in the sequence, whether it's a sub 0, a sub 1, whatever, but it's got to be the first one. If you can prove that it's true for the first one, and if you can prove that, if you assume that it's true, let me say it this way, if you assume that it's true for the kth one, some k greater than or equal to a, if that property is true, if you can prove that it would then be true for the next one, the p of k plus 1 is true, then we're going to say that it's true for all of them. The way we tackle these proofs is shown in the blue box on page 247. It's always a two-step procedure. We say we're going to be doing the proof by induction, and then we do the first step, which is called the basis step. And we show that the property is true for the very first one. Then we show that it's true for the inductive step. We assume it's true for any randomly chosen k in the sequence. So we assume it's true for k, and we show it's true for the next one, the k plus 1th one. And then we can say by the principle of mathematical induction, it's true for all of them. A very common way of thinking of this is to think of it with a collection of dominoes. Dominoes are those little rectangular boxes that, well, most people don't play the game of dominoes with them. There is such a game. But they'll line them up and knock over the first one. And if they're lined up with a proper spacing between all of them, then the entire collection will go down. The way that this is analogous to mathematical induction is knocking over the first domino is equivalent to the basis step. If you can prove that it's possible to knock over the first domino, you're the first part of the way there and you've done the basis step. For the inductive step, what we want to do is we want to assume that our property is true for the kth domino. We're going to assume we can knock over the kth one. And then we're going to prove that we can knock this over for the very next one, the p of k plus 1. Then we say, because we were able in the basis step to knock over the first one, and in the inductive step, that when we knock over the kth one, we can knock over the one after it, the k plus 1th one. Then we can say by the principle of mathematical induction This property is true for all the n's starting at our first one. In the next video, we're going to look at a famous example of being able to do mathematical induction.